So, the last thing we left off with here was the realization, or just remembering that all of this exercise, you need to do the experiment to know what the rate law is. You can't infer what the rate law is directly just by looking at the balanced equation. Okay. Now, it turns out, in this particular example, the rate law does match with the coefficients. Okay, you see that? I don't have a pointer here. But 2NO plus 1O2 goes to 2NO2. And in our rate law, we have O2 first order and NO second order. So that matches the coefficients of our balanced equation. Okay? So what I have written on here in green is true. You can't look just at the balanced equation and infer what the rate law is. But, this is a big but, okay? Once you've done the experiment and you get the rate law, you can then say, hey, you know what? That supports the model that it really is 2 molecules of NO colliding with 1 molecule of O2 to have the reaction go. That's a big difference, okay? And we're going to be doing that later on. We're going to be making some hypotheses. What do we think the actual mechanism is? And then once we generate the data, we'll be able to use the rate laws to determine which proposed mechanism is the most likely correct one. Doesn't prove it. It's just consistent with. Most everything you do in science when you do experiments is you're finding what's consistent with your hypothesis. You're not really proving it. You can disprove it, but you can't really prove it. It's just more and more likely that it's correct. That's a little bit of legalese for scientific speak. All right, hopefully I've really impressed that on you. So do I have any words to put in here? Yeah, sure, let's put this into words. Okay, so this is true. Okay, but then let's add to this, but if the molecular mechanism matches the stoichiometry, then here's for all your computer scientists out there, if-then statement, right? Then the rate law will match the stoichiometry. Then the experimentally derived rate law will match the stoichiometry. Stoichiometry. Now, even writing it out, it looks confusing, okay? But leave it there in your notes, okay? Because when we get there, and then when you start reviewing things, you'll see this in your notes, and you go, oh, yeah, that does make sense now. All right, so K is still a mystery, all right? We haven't really explored what's underneath K. I talked about it a little bit the last time, right? But it's part of all of these rate laws that we've been calculating from the experimental data. So here in these tables are the 3 experimental data sets that we've been using, all right? And I'm going to use these now to make a point, because once you've determined what the rate law is, you can actually calculate the numerical value of K from your experimental data. And it's really just algebra. So if I remind you, for example, that the rate law, it's the rate is equal to K times, and for this first reaction, right, which is tiny written up here, all right, if you go back in your notes, you'll realize that the rate law that we determined from that experimental data was first order with respect to ozone and first order with respect to nitrogen monoxide. So that's the rate law that we derived from the data, okay? But from that now, we can actually calculate what K is, because we can look at our table and we know what the rate is. Here's the rate. And we know what the concentrations are. So all you have to do is just pick one of those experimental trials, and it doesn't matter which one. I'll just pick number 2 because that's what my notes say. But this will work on any of them. I mean, within experimental error. That's why, again, in the real world, you have to repeat your experiment. Okay? But this isn't the real world. It's just an example. So what I'm about to show you will work on any 3 of these data sets. But you got to be consistent and just work with one. So let's just rearrange this. K is our unknown. All right? So K is equal to the rate divided by the concentration of ozone times the concentration of NO. It's that simple. And now you just plug and chug. The rate for reaction 2 was 22, and that's molar per second. Remember, the units of rate is always molar per second. And we divide that by the concentration, the initial concentration of ozone in experimental trial 2. That was 0.002 molar, multiplied by the concentration of the initial concentration of NO in experiment 2. That was 0.001 molar. Okay? And there's no exponents there. It's all first order. So you work out, you got like 1.1 times 10 to the 7th, right?
Yeah.
Right, yeah. That's what my notes say. Now, what are the units on that? Well, take a look. Let's see what cancels out. Molar cancels with molar, and we have per second numerator, and we have divided by molar. So the units here are going to be, let's do it molar first. It's going to be per molar per second. But that's what K is. Now again, you still don't know what K represents. We'll look at that later. But you can calculate it. And this is just another example of taking a equation that we learned how to do initially from left to right, but once you know the equation, you can take any variable in that equation and make it an unknown, and using algebra you solve for the unknown. I expect every one of you to be able to do that kind of simple algebraic rearrangement. Even if we haven't done that example specifically, when you're studying this stuff and you're studying a plug and chug in a reaction or in an equation, go ahead and practice. Make one of those variables an unknown and do some algebra and solve for it. Practice, practice. All right, let's practice. Let's do it for this next reaction. Should I let you do it, or should I just? I'll just show you. I do want you guys to do some work, but I think there's more examples coming up for you to do on other things. So let's save a little bit of time. So the rate law for this next reaction here we calculated was equal to K times the concentration of oxygen, first order, times the concentration of nitrogen monoxide, second order. So what's K? Here, you can calculate K. Again, my notes are using trial 2. But with this kind of data, you can get the same answer from any trial. The statistics.
Once it's gone through that much math, it's like meaningless anyway.
All right. I got my answer up here. Does yours agree? Who got 0.99? Who didn't get 0.99? All right. So let's figure out why, right? Actually, here's the plug and chug. Just plug the numbers in. Chances are you set it up right and you just, I don't know, didn't enter it in the calculator correctly. But hopefully your setup should look like this. It's just the rate divided by the concentrations, but now, or maybe you didn't raise it to the second power. You got to pay attention to the rate law. Okay? We got the rate law from this data, but now when we calculate K, we've got to plug in. So the concentration of NO, whoops, I squared the wrong thing. Wait, did I?
Yeah.
Yeah, I squared the wrong thing. Did I calculate it wrong then? Let's keep things parallel here. What's squared? NO is squared, but NO is the 0.25, so that's here. Let me swap these around. This is what it should look like. Yes? because it's the concentration of O2, which was 0.066, okay? And this is the concentration of NO, but we have to square it. So I might have calculated this with the wrong. So what's the right? I didn't bring my calculator with me.
That's the answer I got.
Is that what you got?
Yeah, that was the right answer.
So this is right. Okay. So I just set it up wrong. All right, is everyone clear on what happened? Because I had to do a little bit of razzle dazzle. All right, this is K. But look at the units. Look at the units. Molar cancels with molar, and what's left is the inverse of molar squared now, because this molar squared, and the inverse of seconds. The units have changed, but it's still K. Overall, this top reaction, what's the order of the reaction overall for the top reaction? First, second, third, fourth?
Which one?
For the top reaction. What's the overall order? That's where we take a look at, we add up the superscripts. So overall, this is second order. Overall, this one is what? What's the order of this reaction? Third order. And notice that the units have changed. The only reason the units change is because the units of rate are always going to be molar per second. Always. That's why the number that's written on top is molar per second. That never changes. That's the rate. But K is going to change depending on the order of the reaction because of how we do the math. All right? Let's do the last one. You guys do it. What's K for this last one? I'll just tell you, go ahead and use this data. Oh, I have to tell you what the rate law was so you don't look it up. So the rate law for this last one was zero order for carbon monoxide and second order for NO2. Okay? Everyone got the right answer? Or at least got the same answer that I got? Hopefully. What are the units?
Just S.
Molar cancels with one of the molars down below, all right? But not both of them. Remember, it's m squared in the denominator. So the units here are going to be per molar per second, which are the same units as that we have on top for second order overall. Is this reaction second order overall? It is, because look at the rate law. All right? So we're second order, so everything's good. Okay? So it's really a two-step process. If you want to calculate K from data like this, you have to first interpret the data, experiment by experiment in pairs to figure out what the rate law is, and then you go back to one of the experimental trials and plug that data in to calculate K. It's really simple and straightforward. It's just now you've got two-step process to keep in mind. So let's talk about another way that we can look at first order, second order, and zero order kinetics using what's called the integrated rate laws. Okay, this is it's a completely different way to address the same question, looking at different kinds of data. This works really well for reactions that depend on only one reactant. And all we need to do is we just measure the change in the concentration of that reactant. Let's call it A, okay? We measure the change in the concentration versus the rate, and we then integrate that over time. Now, this is not a calculus class, which is good because I don't even remember the calculus needed to do this, okay? That's how long it's been since I've taken calculus. Maybe some of you can do this, right? But I'm going to at least show you where these integrated rate laws come from without actually doing the calculus, okay? Because I do like showing you a little bit about the derivation of these things, rather than just say, here's an equation, now use it. Right? Here's a rate law for first order rate kinetics. Agreed? Yeah, we all know what that looks like. So if we take this and we integrate that, as I said, right, measure the concentration of A, and then integrate over time the concentration of A versus the rate, okay? So let's integrate this. What you get then is something that looks like this. The natural log of the concentration of A at any time t divided by the initial concentration that we started with is equal to negative K times T. And again, what we're integrating here is the concentration of A at any times T, actually concentration of A at 0 to at any time T, right? That's what we're integrating here. All right, so when we get that, all we need to do is a simple rearrangement, but that simple rearrangement does require you to remember a couple things about logarithms. So when you have a natural log of A times B, that's equal to the natural log of A plus the natural log of B. It doesn't have to be natural log. This works with log base 10 as well. Okay. If we take the natural log of A divided by B, that's going to be equal to the natural log of A minus the natural log of B. Okay. And let's see, how about anti-logs? Who remembers anti-logs? The natural log of A, remember natural log, what's the base of the natural log? E. What does E stand for? Euler's number. All right, so that's base E. So if we want to know what A is, A is E raised to the natural log of E to the A. That's what it is. There. Does that look better? Yeah. Remember these. They can be useful to you. This is called an anti-log. You do this all the time with pH. We'll be doing that later on in the semester as well. So this isn't going away, okay? So let's go ahead and apply this one here, okay? That then rearranges to the natural log of A at time t, concentration of A times t, minus the natural log of concentration of A initially is equal to minus KT. And then a little bit more rearranging, okay? The natural log of A at times t is equal to minus KT plus the natural log of A sub 0. Okay? Nothing up my sleeves. Did you see what I did? Does anybody recognize the format of this last equation here? Say it louder.
Y equals mx plus b.
Y equals mx plus b. What does that describe? A line, a straight line. Most of the mathematical mumbo jumbo that we do in this class is putting things in a straight line because it's really easy to work with a straight line. You can get lots of information, like from the slope or the y-intercept. That's what b is. X and y are your coordinates. M is the slope. B is the y-intercept. Do I need to write that on your slide?
No.
Are you sure?
We got it.
All right, cool. So let's take a look then. Let's plot that out. Okay, the y-axis is going to be the natural log of A at any time t, and the x-axis is x, that's t, that's time. Okay, and the slope is negative k, so we have a negative slope. That looks like this. And the negative slope, that equals minus k. All right? So what this means is you collect your data up here in the upper right-hand corner. Just measure, as I could do, just measure the change in concentration versus the rate over time, all right? Really, it's just the concentration over time. I don't know why I have rate there. Really, the changing concentration over time is what we're doing, okay? And you plot it out, and you do some linear regression, all right? And you see, is it a straight line? And if it's a straight line, and the data that you've plotted is the natural log of A versus time, and it's a negative slope, that's consistent with it following first order rate kinetics. Okay? Now let me switch colors here just to show you. If it's zero order, right, here's the rate law for zero order. If we do the same thing, okay, I'm not going to show you the whole derivation, right? But the end result, if we do the same treatment, we get a straight line, but now the equation is the concentration of A, not the natural log of it, but just the concentration of A at any time t is equal to minus kT plus the initial concentration of A. That's what it looks like. If we do it for second order, okay, it looks like this. 1 over the concentration of A at any time t is equal to positive kT plus 1 over the initial concentration of A. You have to know what these mean and how to use them. How you would use them is, well, let's take a look. How do I get a straight line if it's second order kinetics? Well, if it's second order kinetics and I plot 1 over the concentration of A at any time t versus time, then I expect to get a straight line with a positive slope. And here the slope is equal to positive k. If I collect my data and plot instead, I plot just the concentration of A at any time t versus time. If it's following zero order kinetics, then I expect to see a straight line with a negative slope. Okay? Now, where this becomes useful is before you start an experiment, you don't know if it's zero order, first order, or second order. So you just go ahead and you collect your data and you plot it all three ways. You plot the concentration at any time t versus time. You plot the natural log of the concentration at any time t versus time. And you plot 1 over the concentration of t versus time. And then you ask, do any of these give me a straight line with the expected slope? And if they do, then it's consistent with it following zero order, first order, or second order kinetics. You are given these. So here they are, all right? This is just a figure from your textbook. Right? Here's the integrated rate law for zero order. Here it is for first order. Here it is for second order. You can tell right from them what you expect the slope to be. You have to know how to recognize a negative slope from a positive slope. Okay? Now down below, all right, half-life expressions. We're going to talk a little bit about half-lives probably next lecture, okay? We're only going to be focusing on half-lives for first-order reactions. We're not going to consider these down here. Okay, so what this looks like, all right? Here's just an example. Here's some data. We're going to follow the conversion of ozone to molecular oxygen and a free radical of oxygen. Okay. And here's the data on the right. We're not going to spend a lot of time on this. Right? We're not going to crunch through it. But you would generate this data and then you would plot it. Here we're just seeing two plots. So what you want to look for here is what are on the axes of these plots. Time is always on the x-axis. What's on the y-axis? Concentration and the natural log of the concentration. Which one gives you a straight line?
Natural log.
Right, the natural log. So this is natural log. So what order reaction is it? second, first, or 0? It's first. If it's second, it's 1 over the concentration. If it's 0 order, it's just the concentration. If it's the natural log of the concentration, it's first order. But it's got to be a straight line, all right? So here, from the textbook, it's using, actually, that's just telling you what the slope is. It's not doing linear regression here. But you can tell that that's a straight line, okay? Versus this, which is clearly a curve, all right? So from our straight line, what we care about, if we wanted to calculate K is right here. K is negative. Now, I know I said earlier it's negative K. Don't get confused with the swapping of the signs, okay? This is K, but K has a negative value. It's a negative slope. So the value of K is negative blah, 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 blah. Here's another example. This is a second order reaction. Oh, there, yeah, the answer to my question was at the top of the slide, wasn't it? Here's second order. Once again, you collect data, you plot it 3 different ways, and you ask which is linear. This one is linear, so that's going to be consistent with the rate law, with the order of the reaction. In this case, it's 1 over the concentration of NO2, so that's consistent with second order. Notice here the slope is positive. All right? Visually, that's all it's about. Okay? So the only other thing you need to understand then is how to apply this to a problem that you might see on, say, I don't know, the homework assignment, or in the back of the text, in the back of the chapter. So let's take a look at that. Let's do some practice. All right, so let's extract the information we need from here. Blah, 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 blah. We don't really need temperature here. Here's our equation. We're told, here's some key information. We're told it's first order. We're given K. And we're asked how much dinitrogen tetroxide, that's what that's called, remains in solution after 1 hour if the initial concentration, so that's going to be N2O5, 0, that's our initial concentration, is that. Let's not worry about the second question. Let's just concentrate on the first one. How much remains? Now look at the information that we're given. We're told it's first order. We're told the initial concentration. We're told K. That smells like integrated rate law for first order. So let's write that down. It's going to be the concentration of N2O5 at some time t is equal to minus KT plus, natural log. I left that out. Plus the natural log of N2O5 initially at time 0. And now let's plug in the values that we know. So this is going to be the natural log of 0.50 molar, right? That's initial. We're told what K is. K is minus, and it's 6.32 times 10 to the minus 4th per second. Notice that K is in per second. So if you look back on that chart, that should be the units of K for a first order reaction. We need to solve for T. No, we don't need to solve for T. We're told what T is. What's T?
An hour.
It's an hour. So what am I going to put here for T? 1 hour? Units don't cancel. If I put 1 hour here,
50 seconds.
3,600. Very good.
I think per second.
3,600 seconds. Now our units cancel. Thank you very much. All right. So that's going to be all equal to the natural log of N2O5 at 3,600 seconds. So instead of putting sub t, we're at 3,600 seconds here. And that's what we're asked to solve, right? How much remains? This is our unknown, so that's x. So the log of x is equal to, now we have to get our calculators out and figure out what all that is. I did it already, so, and I didn't bring my calculator with me, so I just have to tell you what's in my notes. So, this is minus 2.275, and this value, the log, natural log of 0.5 is negative 0.693, okay? Now here are the units canceled out, and here the units are molar. So that gives us then, what's this now? Minus 2.968? Yeah, good. So the natural log of x is equal to this, but we want x. We don't want the natural log of x. So that's where we need to take the anti-log. X is going to be equal to e raised to the power of negative 2.968, which is, I have in my notes, 0.051, and we have our units of molar. That should be the answer. Now we haven't answered the second question here. What percent has reacted at that point? But that's easy to calculate now, because at that time, right, at 3,600 seconds, we have 0.051 molar is left, and we started with 0.5 molar. That's initially. So from that you can calculate, times 100. You can calculate what percent remains, and it's about 10%. That's just a little add-on. The main learning outcome for solving a problem like this using the integrated rate law is all in here. It's just a bunch of math, right? It's algebra. But you should know how to do this math. You'll be given the equation. You have to know which equation to use. You have to be able to recognize what you need. But then you just punch the numbers in. And then, like I said earlier, once you get used to that, practice making any one of these your unknown, and rearrange it so that you can solve for the unknown. That's really all there is to this stuff. All right, so here is another integrated rate law problem. You're given the reaction. Here's the question: how long for the concentration of this reactant, to equal 0.11 molar? And you're given the initial concentration of 0.88 molar, and you're given the rate constant, and you are told that when you plot the natural logarithm of its concentration versus time, you get a straight line. Really what it should say is you get a straight line with a negative slope. All right, because if you get a straight line but it's a positive slope, that's not consistent with what order rate reaction is this describing using the integrated rate laws? 0, 1, or 2?
Negative 2.
It's 1, because it's the natural log of the concentration. So we know then we want to use this equation, the natural log of C5H6 at some time t is going to be equal to minus KT plus the natural log of C5H6 at initial concentration. And now let's just plug the numbers in. We know what K is. We want to solve for, what do we want to solve for? T. Because we know what the concentration at time T is. That's 0.11. So it's going to be the natural log of 0.11 is equal to minus K, which is 0.254 per second, times T, plus the natural log of the initial concentration, which is 0.88.
That's supposed to be 0.245.
What is it? Sorry. Yes, thank you. Okay? And that's it. That's all it is. Once you recognize it, you plug it in. Now it's just algebra. Do I need to solve this for you? You've got it in your notes. I'll go ahead and solve it so that to make sure that when you practice it, you know how to use your calculator the right way. But this is just rearrange. T is equal to the log of 0.11 minus the log of 0.88 divided by negative 0.245. And if you wanted to, you could have taken that numerator and turned it into the log of 0.11 divided by 0.88. But that's one of your identities in logarithms, right? Same thing. There you go. So it's 8.5 seconds. How much is left after 1 minute?
After you did it.
That's the challenging one. How are you going to solve that? Well, think about it. Use the reaction. Use the equation. All the information you need is on this page. Or you can think about, well, what do I need? What information do I need to calculate how much is left? You know how much you're starting with. You know what K is. And now you know what T is. And you want to calculate how much is left at time T.
Someone else got it.
All right. Or whatever that is, right? Let's just set all this up. We know the initial concentration, right? That's 0.88 molar. And we know K. K is 0.245 per second. And we're asked for T after 1 minute, but let's get that into seconds because K is in per second, all right? And so we want to know what the concentration of C5H6 is at 60 seconds. That's going to be equal to minus K, which is minus 0.245 per second times 60 seconds, plus the natural log of the initial concentration, which is 0.88. When you did all that, you all got, what was it, minus 14.83? Thank you. All right, but that's the natural log of C5H6 at 60 seconds. So to get what the concentration is, C5H6 at 60 seconds, we need to take the antilog of that, 14, e to the power of negative 14.83. And that gives us 3.6 times 10 to the minus 7th molar, which is really, 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 really tiny. Okay? But that's consistent. Oh, that's fine. That's after a minute. So this reaction goes really, really quickly. The kinetics of this reaction is really fast. So after a minute, almost all of it's gone. Now, if I wanted to, I could make a third question out of this. What percent remains? Or anything, right? You can make up anything now. What percent remains? Well, after 1 minute, we've got this molar. We started with 0.88, so what's that percentage? Et cetera, et cetera. Okay? That's really what all these are about. Now, I've only been showing you examples of first-order rate kinetics. So when you practice this, practice it with a problem that's zero order or second order, okay? There's a reason we stick mostly with first order, and that's because a lot of the reactions that occur that some people care a lot about follow first-order rate kinetics. And that's also why we're going to talk about half-life right now, because things that follow first-order rate kinetics, we can use the integrated rate law to calculate what the half-lives are very, very easily. Now, if you look on that summary slide a few slides ago, okay, you will see that there's a little equation at the bottom of the half-life. T of the half-life is equal to 0.693 divided by K. But I'm going to spend a little bit of time to show you where that comes from, because I think it's important to at least see how these things were derived. But before I do that, let's just talk a little bit about the things we care about that follow first-order rate kinetics. And by the way, when we say first-order rate kinetics, that means that whatever the half-life is, whatever we specify, like let's say it's, in this example, it's 1 day. All right? So in this example, after 1 day, if we start with 16 molecules, after one half-life, after 1 day, now we're down to 8. So in one half-life, half of the material has gone. It's either dissipated or it's reacted or it's decomposed or whatever. Okay? And then another half-life, another day or or whatever that is, seconds in this case. And now we've reduced it from 8 to 4. Okay? And then another one, and so on and so forth. That's just what the simple definition of a half-life is. Lots of things follow first-order kinetics as they decay. By the way, here's just your formal definitions up here. For example, the degradation of pesticides, radioactive decay, drug metabolism. These are things we care about a lot. If you take a drug, like let's say you take some acetaminophen, which is not quite what acetyl salicylic acid is. That's just aspirin, isn't it? Yeah. Acetaminophen is something else. Well, you take some aspirin, and you want to, why is the dosing that you have to take it every 4 hours? Because it breaks down in your body. Here's the reaction that it breaks down, and the degradation of it in your bloodstream follows first order rate kinetics. If you've got you're doing some radioactivity, let's say in the laboratory, and you're using some radioactive phosphorus 32, you're doing some DNA labeling work or something, P32, that has a half-life of about 14 days. Or you might be radioactively labeling some proteins with sulfur, S35. That's also radioactive. These are radioactive isotopes. S35 has a half-life of around 87 days. So if you've got some radioactive P32 sitting around the laboratory and you don't want it to hurt anybody, well, just let it sit there, come back in 2 weeks, and half of whatever you had, has now decayed into something that's stable and safe. All right? And if you come back in 2 more weeks, then half of that. All right? So you can calculate, when can I go back into the laboratory and it's safe to go ahead and clean it up now? And then it's perfectly safe. For S35, you got to wait a little bit longer. For you archaeologists out there, right, you want to do some carbon-14 dating, right? We already used that as an example. What's the half-life of carbon-14, which is also radioactive? Remember? Anyone remember? It's about go ahead.
5,700 days.
5,700 years, not days. Did you say days? Yeah, it's years. It takes a long time for that to decay. But it also follows first-order rate kinetics. And you can see all of that here, okay? Here's aspirin, okay? Here's the same data, right? Here's the time. As we follow the time, we look at the concentration of the aspirin that's left. All right, if we were to plot just that, look at the y-axis here. Here we're plotting just the concentration of the aspirin versus time. It's not linear. All right, it looks like a curve. Whereas if we plot the natural log of it, we get a straight line with a negative slope. Negative slope, and we know that that negative slope is equal to k. So we can actually calculate what k is from that negative slope. So let me actually derive this for you really, really quickly. T half-life is equal to 0.693 divided by k. So this is all first-order rate kinetics. Now, for the half-life, what we're going to really be doing here, all right, in one half-life, we're going to say, okay, we need the time that A sub t is equal to 1/2 of the initial concentration. That's another way of just mathematically stating what it is that we're doing, right? We need t, where the concentration at time t is half of what we started with. So this is following first order. And let's just write that down. We'll just keep using a as our variable here. So that's the natural log of concentration of A at times t. Time t is equal to minus kt plus the natural log of the initial concentration of A. And now I'm going to substitute that in. okay? A sub t, I'm now going to substitute in 1/2 A initial, okay? So let's substitute. Instead of writing it as 1/2, I'm just going to write the natural log of 0.5 A initial is equal to minus KT plus the natural log of A initial. Into here. I just changed A sub t to 0.5 A sub 0. And now all I need to do is creatively rearrange things. Let's bring the natural log terms all together. Right? That's the natural log of 0.5 A sub 0 minus the natural log of A sub 0 is equal to minus KT. And then let's use that trick with logarithms that we did before. That's the same as the natural log of 0.5 A sub 0 divided by A sub 0 is equal to minus KT. And by the way, now that we're doing this, this is T 1/2. This is the T half-life. Because once I made that substitution, T becomes the time for this concentration to be half of what we started with. Now everything's in terms of A sub 0, so that cancels out. Whatever the initial concentration was, it cancels out. And what we're left with then is the natural log of 0.5 is equal to minus KT. And if you punch in your calculator, what's the natural log of 0.5?
Would that T be also half or no?
Negative 0.693. That's equal to minus K T 1/2. So rearranging then, T 1/2 is equal to 0 plus 0.693 divided by K. You don't have to understand that, but if you don't, then you just accept this magical equation and you use it in a plug and chug, and you get your 3 points on your exam question, and then you walk away as if you didn't know any better, right? But if you understand this derivation, and you're ever challenged to like, oh, maybe somebody didn't give me the equation, but they did give me the integrated rate law, I know how to derive this. It's not that hard. A few of the things that we do in this class, I want to show you this because it's actually not that hard to derive from the original equations that we work with. All right, now, knowing that, we can solve this typical half-life equation. Here's a radioactive isotope, P32. It decays by first-order rate kinetics, and it has a half-life of 14.3 days. How long does it take for 95% of the sample to decay? So let's decode this a little bit. We know what T 1/2 is. That's 14.3 days. But for our overall equation, this is a first order rate law equation. So really we want to be working with, this equation. And T 1/2 isn't in there, but we need K. And we can get K if we have T 1/2 because we have this relationship. So anytime you're working with a half-life equation like this, or half-life problem like this, and you're given the half-life, just go ahead and get it into K. Figure out what K is, and once you know what K is, you can then it just turns into a standard first-order rate kinetics equation like we've been doing with the integrated rate law. So let's do that first, all right? T 1/2, right, that's going to be equal to 0.693 divided by K. So what does K equal? K is equal to 0.693 divided by 14.3 days. All right, so now we know what K is. Now we can plug everything in. So now we've got, one more thing to do. All right, we need the time it takes for 95% of the sample to decay. So how much is left at this time? How much is left? 5% is left. Which percent, convert that back into a decimal, that's 0.05 molar. So that's what's left. That's what we need for our concentration at time t. So now we can plug it all in. Natural log of 0.05 is equal to negative 0.0485 per day. And we want to solve for t. How long does it take? And then we've got the initial concentration, which was... What's the initial concentration? Oh.
Never found it.
Oh yeah, this is cool. 0.5% is left. Sorry, I put it 0.05 molar. That's not right. That's not right at all. Because we don't know what the starting one is. All we know is that 5% of it is left. You see the difference? Okay, so let's fix this. How would you fix this? You said that, right? Yeah. Plus the natural log of what we started with. See, now it doesn't matter what we started with. Because the problem is telling us or asking us, doesn't matter how much you start with, we want the time for 0.05 of it to be left. Or 5% of it to be left. And all we really needed to do was solve for what K was. That was really the only missing link here. Now we can do the same trick that we did before. Right? Natural log of 0.05 A sub 0 minus the natural log of A sub 0 is equal to minus 0.0485 T. That's the same as the natural log of 0.05 A sub 0 divided by A sub 0 is equal to minus 0.0485 T. These cancel out. Now we have natural log of 0.05 is equal to minus 0.0485 T. So T is equal to the natural log of 0.05 divided by negative 0.0485. And as you're doing this, you might think, wait a minute, time, if there's a negative sign here, we can't have negative time. That doesn't make sense. But when you do these enough, you'll realize that when you take the logarithm of a number that's less than 1, you get a negative value. And that's true whether it's log base 10 or log base e, natural log, okay? So this will give you a positive number for t when you do this. I'll round that to 8, 61.8 days. Okay? I recognize that was a lot of math, all right, and it was fast. But when you review this and learn it, you'll see that it's actually no different from the math we were doing before. It's no different from just looking at the integrated rate law for first order rate kinetics. And we just put this little twist in there of the half-life. So if you have a half-life question, let me put this in fuchsia, bright fuchsia pink. Half-life questions, all right, these are usually 2 steps. You want to look for 2 steps. Because you have to make sure that you have all the information you need to use the integrated rate law, all right? And usually, in a half-life question, you're just given the half-life, so you need to calculate K. Then you can just do this as any other type of question. Okay? Let's now finally get back to that mystery of K. What is K? What is the rate constant? What's it all about? Okay? And I talked about this briefly, all right? And it says it right here in the subheading. It's all about the orientation, the activation energy, and the temperature. And these are things that we want to now think about because that's going to dictate that K, right? That's going to dictate how fast a reaction can go. Obviously, there's some component of kinetic energy. As you increase the temperature, we already talked about this stuff. As you increase the temperature, you increase the frequency of those collisions, right? Because things are moving faster. Kinetic energy, things are moving faster, so the frequency of collisions increases. And the energy of those collisions also increase. right? So this is what happens when we start increasing kinetic energy. And as you recall, just like when we were doing thermodynamics or gas laws and all that stuff, we use temperature as a reflection of the kinetic energy, but then it has to be an absolute temperature. That's in Kelvin. Collectively, all of this stuff, having the right frequency, having the right orientation, all of that stuff, frequency, orientation, and energy, all of that stuff goes into this thing that we're going to call A. And A is called a frequency factor. And it accounts for all of that. We're not going to actually be doing any hard calculations with this, with A. All right? Some classes take you into that. I just want you to kind of know what A stands for, and you're going to see it come up in an equation real soon. All right? But there's something else that we have to account for here, because this is the frequency of productive collisions, not just the frequency of collisions. And that requires the right orientation and the right energy. Only that will give you a productive collision. For example, here's one of the photochemical smog equations that we were looking at. And here's a picture of the reactants. And you've got a molecule of ozone hitting a molecule of nitrogen monoxide. Okay? And you need to have a favorable interaction in the right orientation, and when you do, you make what's called an activated complex here. Let's highlight this. And this activated complex, take a look at it. You've got the bonds are breaking and bonds are forming, and it's all present in the same thing. You might imagine that it's not a very stable complex. And in fact, it's very, very hard to trap these. We imagine that they exist, but it's very, very rare that you can design an experiment where you can actually isolate what this activated complex looks like. There's another name for it, and it's written right down here, a transition state. I'm not going to worry about splitting hairs about the difference between an activated complex and a transition state. I'll just tell you that there are many different activated complexes that all keep going and going until you get to the highest one, which we call the transition state. All right, but you can, in my class, we can think of them as being the same thing. It's a very high energy, unstable complex that has to be made before you can resolve that complex into products. Okay? Sometimes we use a double dagger to represent the activated complex or the transition state. That's the symbol that we typically use. Right? These are very, very unstable. So that means it requires a larger energy for it to exist. Stabilize it. Okay? That energy, this is what we call the activation energy. And we use E sub A for our activation energy. All right? So K collectively has all of these components in it. K has an A factor component, it has an energy activation component, it has a temperature component. Those are all part of K. wanted to discuss those three things first. So you had at least an idea of what they meant. You have to have the right orientation and the right energy. Things have to meet in the right way. And when they do meet in the right way, you still need to have enough energy to make that activated complex. Because if you can't make the activated complex, it will never resolve into products. Now, it could also resolve back into reactants too, as you'll see. What we're talking about here, let's just take a look at it. Here's a curve, all right, where we have the progress of the reaction in the x-axis. This is what I've been calling the reaction coordinate, where we start with all reactants on the left side and all products on the right-hand side. Okay, we've got some energy here. It doesn't matter what that energy is. This could be free energy. It could be enthalpy. It could be potential energy, whatever. All right, we're just talking about energy here in a generic sense. Here's your activation energy. That's the energy that you have to overcome. The reactants, they need to meet some correct orientation with enough energy to be able to make the transition state. Okay, let's just say this requires correct orientation, energy, etc., right? That's what A is. And once it's there at the top of the hill, now that's that unstable transition state with all the bonds in some metaphysical state where the bonds are half made and half broken, and we can only imagine it, but it takes so much energy to really keep it stable. Activation energy, all right? But once you're there at the top of the hill, you can roll backwards and form reactants again, or finally, once you're at the top of the hill, you can go forward, fall forward, and turn into products. So if you don't have enough energy in the system, you're never going to make it to the top of the hill. Once you're at the top of the hill, now you can resolve either way, because whether you resolve backwards or forwards, you're going to come back down to a lower energy level. Okay, so let's look at the bottom slide here, which is very similar, but now we have something slightly different. Here we can change things like change the temperature. For example, what would happen if we increased the temperature? Empirically, what do you think that's going to do to the system if we increase the temperature? Is it going to make things go faster or make things go slower?
Faster.
Make them go faster, right? Increasing the temperatures, increasing the kinetic energy of the molecules, so you have more collisions. So there's a greater probability that those collisions will be favorable. That's A, okay, your A factor. And they're more energetic collisions, so they already have more energy. So that's going to lower the activation energy. Because now you have more energy in the collisions, and so you don't need as much extra energy in the system to get to the same transition state. If you increase the concentration of the reactants, right, that's also going to increase the probability that you're going to get the right collisions with the right orientation. All sorts of ways that we can reduce the activation energy here. We can also add a catalyst. We talked about that at the very beginning. Adding a catalyst will also lower the activation energy. But we're not going to talk about catalysts until the end of this chapter. So that's still coming soon to a lecture near you. What do you notice really interesting about this reaction? Even though we can change the activation energy, right? But what do you notice is going on here?
The energy of the reactants and products are the same.
Yeah, the reactants and the products are the same. Where these are, don't change. Why is that? Why don't these change? This is delta G, or delta H, or potential energy, or anything like that. What do you remember about those values? They are state functions. And what does that mean that these are state functions? Yeah. It doesn't matter what path you take to get there. You're moving from, and now I'm going to really overlay this heavily, all right? You're moving from equilibrium state 1 to equilibrium state 2. And it doesn't matter how high of a hill you have to climb. It doesn't matter how high that activation energy is, or if you add a catalyst, or if you increase the temperature, or you do anything else that changes the activation energy, the difference, the delta, stays the same, right? So this delta is the same regardless.